Welcome everybody. In today's video, we are going to finish up chapter 8. So let me share my screen. We are going to cover carbenes, radical reactions to alkenes, and then cover a little bit about just overall stereochemistry of alkene reactions. Then there's going to be a brief summary, just because we've covered a lot of different types of reactions with alkenes. So the first section is talking about cyclopropane synthesis. So here's our cyclopropane ring. And to synthesize that, what we use is a reagent that can generate what's called a carbene. So a carbene is a really special type of compound. It is a carbon that has a lone pair and two other groups. So what's really interesting is that, notice, there is no negative charge to this. So this is not a carbanion. This is an electrophilic carbon just because it only has 6 electrons around it. So it's electrophilic, but also has a little bit of, if once it's bonded to something, has a little bit of a nucleophilic character here with the lone pair. It is neutral and it has 3 main groups, so 1, 2 attached and a lone pair. So that makes it sp2 hybridized. It's very reactive. So once you generate that in a reaction mixture, that will be very reactive to go on and generate your cyclopropane. So there are 2 main ways I'm going to talk about how you synthesize a carbene. The first is using diazomethane. So this group here with 2 nitrogens is an azo group. Basically, you guys are going to have a carbon attached to that, a methyl group essentially, but without one of the hydrogens. This is one of the resonance structures that you can draw for diazomethane. Basically, you have a resonance structure where nitrogen has a +1 formal charge. It's an N with 4 different bonds. And so one thing that can happen is this can fragment. Basically, the 2 electrons in this bond can just break off and go onto nitrogen as a lone pair, generating and releasing nitrogen gas. What's left over then is your carbon. Since it gave up 2 electrons to nitrogen, it no longer has the -1 formal charge, but it's neutral and it has 6 electrons around it. This is called methylene because it only has 2 H's on a carbon. It's the simplest carbene that you can have. The other type of carbene that you can make is one where you have 2 chlorines on it, a chlorocarbene. The way that we synthesize that is we start with chloroform. So chloroform is CHCl3. And what you could do is you could take a really strong base. You could take hydroxide, you could take butoxide, and you can deprotonate the hydrogen on chloroform. When you deprotonate it, then the electrons in this bond will then jump onto carbon, giving this carbanion species, and then chloride can leave as a chloride leaving group, revealing your dichlorocarbene. Once you have your carbene, you could go on and make cyclopropanes. So in these 2 examples, I'm using diazomethane and heat to generate the carbene. And when you have a carbene and an alkene, basically the pi bond breaks and reacts with this carbon unit. And what you effectively add is the CH2 here onto where the double bond was, forming a 3-membered cyclopropane. So in this case, we have a transalkene. That stereochemistry is preserved. So basically, trans, these groups are opposite each other. So the easiest way to draw that here is draw the cyclopropane, 1 methyl down, 1 methyl up. The other thing that you also have is it's an enantiomer. If you start with the cis alkene, you can do the exact same cyclopropanation, but this time now the 2 methyls are syn to each other. There is no enantiomer in this case. The reason is this is meso, essentially achiral, because there's a plane of symmetry here. And if you did look at its mirror image, if you did try to draw the enantiomer, what you would find is if you just flipped it over or rotated it, you would see that it's actually the same compound. So the key thing here is the cis or trans geometry of the starting alkene will dictate the stereochemistry of the products. If we run the exact same thing with the chloroform tert-butoxide mixture combo, you get the same types of products, the trans product plus it's an enantiomer, but instead of CH2, you have C with 2 chlorines on it in both cases, and cis gives that syn or cis product, both on the same face of the ring plane. Okay, let's look at the mechanism. I already told you that this carbon on the carbene is electrophilic because it only has 6 electrons. We know that the pi bond of an alkene can act as a nucleophile and attack an electrophile. In this case, our carbene is the electrophile. And simultaneously, what occurs is the lone pair of the carbene will then attack where you would think a positive carbocation would be. What actually happens is this is a concerted process. So this isn't stepwise, meaning it doesn't attack. You don't really generate and isolate carbocation and then the carbene comes in. What happens is this occurs simultaneously in a concerted fashion at the same time. The bonds broken, bonds formed occur at the same time to give your cyclopropane product. Okay, so you guys can pause this video and predict the products and write down the products of each of these and take care to draw the appropriate stereochemistry and note if there are any enantiomers or not. Okay, I will go over these. If you have this cyclohexene and you treated it with the chloroform tert-butoxide cocktail, you do get your cyclopropane ring with the 2 chlorines on it. So this can happen where you're either coming from the top face or the bottom face, but even if you drew both of those out, what you would find is that this compound is meso, meaning there is a plane of symmetry here. Those are not separate enantiomers, because if I drew the one with both of these dashed, if I just flip the molecule on its back, it would look identical to this one here. So this is meso. So you would just draw one. This one, however, that's trans, that has an ethyl on one end and a methyl on the other. Under the same conditions, we get this dichlorocyclopropane product, but what you see is we get this trans product or anti-product. So basically, the easiest way to draw this is to draw the cyclopropane flat, and then you could do one of the constituents up and down, and either draw the enantiomer or you can write plus enantiomer. Okay, so our next section in this video is talking about the synthesis of polymers. This is a really important process because it's responsible for making a lot of the materials that are out there. For example, polystyrene or Teflon. So let me just break it down for you. Basically, a lot of these materials, plastics, others, they're made of repeating units of what's called a monomer. And the easiest way to synthesize this in a very rapid fashion is to utilize radical chemistry. So we've already had a little preview of radicals. We looked at the halogenation of methane. We're going to look more at radicals in chapter 10. But basically, what we do is we can use one of these types of monomers, initiate a radical reaction, and just continually add on via radical chemistry each monomer until you get the polymer of desired density, desired length, desired mass. Just to remind you, there are the 3 steps of the radical reactions: the initiation, propagation, in this case we call it polymerization, and termination. So in this example, initiation is just generating the radical to just get this reaction kick-started. Here I have benzoyl peroxide, and basically this can fragment. Usually heat or light is used to initiate radical reactions, And in this case, we get this benzoyl radical. This can further fragment to release carbon dioxide gas and give us the phenyl radical here. Now we can get started. We can take one of the units that we want to polymerize and just begin the reaction. So just remember, you have a fishhook arrow going from one of the electrons in this pi bond, kind of in midair, connecting with this radical electron here, leaving one electron on that original alkene carbon center. So after one addition, you get this intermediate. You can do it again to get this intermediate and keep the chain going until you want to get to the desired length. So that's your propagation phase, specifically polymerization in our case. To terminate the radical reaction, basically any two radicals joining kills the reaction. So two radicals here stops the chain growth. Okay, our third part of today's lecture is to talk about just stereochemistry. So you guys have done a lot of different reactions. Some of these give very specific anti or syn products. So we're going to take a look at that. And we're going to take a look at two cases. One case where you start with an achiral alkene, the other where you have some chirality already built into that substrate. So this is an example of an achiral alkene, no chirality, no stereocenters. However, if I want to run a hydrohalogenation using HCl, this goes via a Markovnikov addition to produce the more stable, in our case, tertiary carbocation. So basically you break the pi bond, add the H, you have a carbocation at this carbon center, a tertiary carbocation, which is a good one, very stable, and then the chloride will come in and attack here. So overall, Markovnikov addition is the chloride, in our case, is adding to the more substituted carbon. You get the chlorine here. You will also get this product though. The chlorine is in the same place, so that's same regiochemistry. The chlorine is not here, but since this is a stereocenter, what we're generating are two different enantiomers. How do I know it's a stereocenter? I've got a carbon with 1, 2, 3, 4 different groups. So that means the chloride could add from the top face or the bottom. Is there any preference? Let's take a look. The intermediate carbocation, which has a positive charge on this carbon, has 3 groups and a vacant p orbital. So 3 groups leads us to an sp2 hybridization, and it has this available p that's empty that can receive this lone pair from chlorine to make the new CCl bond. There is no preference to go from the top or the bottom. So you get both. You get Cl up and you get Cl down. That's why we get a mixture of enantiomers, a 50-50 mixture. We also call that a racemic mixture. What if we already have a chiral center? So here I have a cyclohexene, and it already has a methyl group here that is a stereocenter, and this methyl group is set up. I don't have up and down. I only have up. So if I went ahead and did a hydrohalogenation, this time with HBr, it'll still go through a Markovnikov addition. So our bromine will add to the more substituted carbon onto the tertiary carbocation. I will get my bromine here, but there, again, there is no preference to come from the top or the bottom. So looking again, similar to the last slide, at my carbocation, and the plus is really here on this carbocation center. I have 3 groups and this vacant p orbital. The bromine can attack from the top or the bottom with equal probability. So I do get bromine up and bromine down. So on the last slide, I didn't have a stereocenter, so those were enantiomers. However, I have this methyl group, which is going to be up in both cases. In this case, this is R. So they're both R because it's set here. We don't interfere or change or modify the stereocenter during the course of the reaction. But over here, the bromine's up The bromine's down, so the relationship is actually diastereomers, not enantiomers. To have enantiomers, all the stereocenters need to invert, meaning R to S, S to R. And this one doesn't change at all between the two. Okay, I did want to talk about one more cool thing. This is about alkene chemistry in your body. So there are a lot of big molecules that have fused ring systems, such as cholesterol here. A lot of the steroids or hormones, testosterone, estrogen, they have a lot of really similar ring structures, fused cyclohexanes or hexenes, and even cyclopentanes. How are they synthesized? Basically from a starting alkene. So this one has numerous double bonds. This is squalene, and there's an enzyme in your body, squalene epoxidase, that's going to epoxidize one of those double bonds. So you guys have seen this already with one of the alkene reactions using, for example, MCPBA. You could generate an epoxide. If you protonate that, you can get a nucleophile to come in and open that up. So basically, this adopts a certain geometry, mainly chair structures. You can use oxidosqualene cyclase to close up the rings. And it's a cascade to generate eventually a precursor to cholesterol. So specifically, you can envision a protonation or activation of the epoxide. This alkene here attacking and opening up the epoxide. Notice it is on that side that has a more stabilized carbocation, and then you just have a cascade of ring closure just due to alkene additions as you go across, revealing a carbocation here. So just something cool that I wanted to show you, that you guys do know this chemistry and you can connect it with some of the biochemistry in your body. Okay, so just to finish up here, let's just take a big step back. You guys have learned a lot of addition reactions. How do you sort that all out in your head? Number one, there is some memorization to do. You basically need to look at certain common groups that you can see and that you can predict what reagents are needed to make those. For example, diols, either anti or syn, or certain types of alcohols. So that's kind of the first thing that you guys need to do. The next thing is really understanding the mechanisms. The reason is it helps you predict the products or helps you synthesize products. Understanding regioselectivity, whether something's going to occur in a Markovnikov or anti-Markovnikov addition. Hydroboration is anti-Markovnikov, away from the bulky group. Also, do certain things add syn or anti? So this is especially relevant when we're talking about making diols. Sometimes we do want them syn, sometimes we want them anti. Just to do a brief review, you guys should be making a little list yourself and just making your own notes on these. Hydrohalogenation occurs via a Markovnikov addition, creating an alcohol. Adding HOH across a double bond, acid catalyzed, that's Markovnikov addition. We use dilute sulfuric acid. There's a case where we want to use mercury. Oxomercuration and demercuration, that's also Markovnikov, but why do we use this special reagent? If you recall, it's one that will not undergo 1,2 hydride shifts or 1,2 methyl shifts. So sometimes you want the shifts, but sometimes you don't. So you can control that by which type of reagent you use. Hydroboration and oxidation, that's when you don't want the Markovnikov product. You don't want the alcohol on the more substituted carbon. Then you have to use hydroboration and oxidation. What if you just want to saturate the alkene? Add HH across the double bond, make an alkane. We use hydrogenation using H2 and a catalyst, a metal catalyst. Adding 2 BRs, again, that's an anti-addition, so those are little notes that you'll make. Making a halohydrin, so a bromohydrin, you would use BR2 in water. So basically, it's the same mechanism as your bromination, going through that bromonium ion, but then we swamp it with water. So water then opens up the ring to give water and bromine anti. You could do this with chlorine to form chlorohydrins as well. Notice the two cocktails to make your anti and syn diols. We just talked about making cyclopropanes. Sometimes you want to add CH2, sometimes you want to add Cl2. So I just made a correction. I noticed this said a 2 here, so go ahead and correct that on your slide. Also, last time we ended with ozonolysis that basically cleaves a double bond, creating carbonyl groups. If you just want ketones and aldehydes, you would use this mix. Sometimes you want carboxylic acids, that's where you would use the potassium permanganate mixture. Okay, this last slide is just a review. You guys can take a look at this. Number 2, I'm not going to test you on right now. We will cover radicals more in chapter 10. All right, I will continue with this series with alkynes next time.